Welcome to this explainer. Today, we're going on a seriously incredible journey. We're going to zoom way, way in. I'm talking past the objects you can hold in your hands, past the individual cells in your body, all the way down to the microscopic, kind of mind-bending realm of quantum waves. But don't worry, we aren't just staying in the abstract here. We're going to see exactly how these invisible, microscopic phenomena directly power the very real, very glowing screens sitting in our pockets right now. It's an amazing story, so let's dive right in.
Think about the device you might be watching this on right now. If it has an OLED screen, the colors you're seeing, that incredibly crisp red, that deep blue, that vibrant green, are remarkably precise. But have you ever wondered what dictates that exact shade of color? Well, what's really fascinating is that the answer actually lies in invisible quantum waves crashing into each other at the atomic level. I know, it sounds straight out of science fiction, but it's actually the foundational reality of modern chemistry and physics.
So, here is our roadmap for today. We'll start with the magic of molecular orbitals, then look at what happens when atomic waves collide. After that, we'll meet our main characters, HOMO and LUMO, look at the semiconductor connection, and finally, see how all of this is powering modern technology. Okay, part 1, the magic of molecular orbitals. To really grasp this whole concept, we first need to shift our perspective. You probably remember those static, rigid lines drawn between atoms from high school chemistry, right? Well, scratch that. In molecular orbital theory, electrons are delocalized. They don't just sit rigidly stuck between two specific atoms. Instead, they exist in these fluid probability clouds, or wave functions, that actually encompass the entire molecule. When atomic orbitals combine, the electrons are shared across the whole structure. It's a much more dynamic, accurate picture of how a molecule actually behaves in the real world. Moving right along to part 2, when atomic waves collide. Because these orbitals are literally wave functions, they act exactly like physical waves. Think of ripples expanding in a pond. When these waves interact, their amplitudes can reinforce each other through what's called constructive interference. This builds up electron density between the nuclei, shielding them and forming a nice, stable, bonding molecular orbital. But if the waves are out of phase, well, destructive interference cancels them out completely. This creates a dead zone, a node with zero electron density. That pushes the nuclei apart, spikes the energy, and forms a highly unstable antibonding orbital. On top of that, these orbital shapes follow some pretty strict symmetry rules. If you invert the molecular orbital right through its center and it looks perfectly identical, all right, section 3, meet HOMO and LUMO. You can think of these two as the active border guards of the molecule. Sitting right at the absolute edge of where electrons live, they're collectively known as the frontier orbitals. First, you have the HOMO, the highest occupied molecular orbital. This is the absolute highest energy level that actually has bound electrons sitting in it, and it acts as an electron donor. Then, right next door, you have the LUMO, the lowest unoccupied molecular orbital. It's the very next energy step up, totally empty and perfectly ready to accept an electron. And here's why this matters. Virtually all the chemical reactions and electron transfers happen right at this specific frontier. Let's walk through how this actually plays out. When a molecule gets hit with a burst of energy, say from light or heat, an electron resting comfortably down in the HOMO absorbs that energy. Instantly, it gets excited and literally jumps the gap into the empty LUMO. Boom! Just like that, the molecule enters an excited state. This fundamental shift completely alters its chemical properties and unlocks entirely new reactions that were just impossible back when it was resting quietly in its ground state. Which brings us to section 4, the semiconductor connection. So, you might be wondering, how does this microscopic chemistry scale up to the big physical materials inside our computers and phones? Well, there's a perfect direct translation to solid-state physics. The HOMO in a single molecule, it behaves exactly like the valence band edge in a semiconductor. That's the highest level holding tightly bound electrons. The LUMO translates directly to the conduction band edge, the lowest empty level where electrons can freely move around and conduct electricity. And that empty space between them, the HOMO LUMO gap, perfectly mirrors a semiconductor's band gap. These aren't just kind of similar ideas, they are parallel frameworks for understanding how materials transport charge. And this is a massive, absolutely crucial takeaway. That specific energy difference between the HOMO and the LUMO, that frontier gap, dictates exactly which wavelengths of light a compound will absorb or emit. If an excited electron jumps back down from the LUMO to the HOMO, it releases energy in the form of light. If you have a wide gap, it releases higher energy, which means bluer light. A narrower gap means lower energy, giving you redder light. This gap is literally the secret recipe that engineers use to perfectly tune how electronic materials interact with light.
And finally, section 5,
powering modern technology.
Bringing this all full circle, manipulating this very frontier gap is exactly how scientists are building our modern world. By carefully engineering materials to have the optimum HOMO LUMO gap, we unlock some truly incredible stuff. Tweaking it allows chemists to design OLEDs, organic light-emitting diodes, that emit the precise red, green, and blue light that makes up the vibrant display on your phone. Tuning it the other way gives us organic photovoltaics and advanced perovskite solar cells that are perfectly aligned to absorb specific wavelengths of sunlight, maximizing how we harvest solar energy. It even makes things like flexible electronics and organic field effect transistors possible. The whole shebang relies on mastering this tiny, microscopic distance between molecular orbitals.
So let's wrap up with a final thought here. We started off talking about abstract probabilities and wave functions interfering with one another. But as we've seen, tuning this invisible frontier of HOMO and LUMO is exactly what lights up those vibrant screens in the palms of our hands today. So the really exciting question is this. As material scientists get better and better at mastering this gap to build ultra-efficient next-generation solar cells, how much closer are we to solving our global energy crises using nothing but invisible atomic waves? It's an absolutely fascinating space to watch. Thank you so much for joining me for this explainer, and keep questioning the science behind the world around you.